Let's go through this exercise then using the 11-step guide. Step 1 was the design objectives, and this was specified as property protection. They want to ensure that the smoke layer is maintained at least 0.5 metres above the stock. Step 2, we needed to determine the design fire size to be adopted using this formula here. QP equals Chi times AS times QF. Put your known variables in there, we give you all the data. You should have got a QP of 8140.5 kilowatts. That is the convective heat release rate to apply in this calculation. So we've got the design fire size. Now let's determine the mass flow rate of smoke using step 3. Firstly, we need to establish whether this is classified as a simple plume or a complex plume. Now, in this case, the design fire is located in the reservoir where it's going to be extracted. So don't forget, that's classified as a simple plume. So we've got a simple plume. Now we need to decide which model to apply. Is it a line plume, corner plume, wall plume, or an axisymmetric plume? Well, as the stores are going to be located covering the whole area, we have to assume worst case scenario and use the model which will result in the greatest mass flow rate. The model, therefore, we're going to apply is the axisymmetric plume. So we've got an axisymmetric plume. Next, we need to decide whether it's a near field or a far field model depending on the clear layer height. Don't forget, if the clear layer height is greater than the longest dimension of the source multiplied by 5, then it's deemed to be a far field model. If not, it's a near field model. Well, in this case, 5 times the longest dimension of the source, which is 4.5 metres, is 22.5, and the clear layer height is only 8.5 metres. Clearly, this is a near field model. And this is the model we're going to have to apply to determine the mass flow rate of smoke. We need to now work out the coefficient, so we've got to work out the coefficient to use, whether it's 0.21 or 0.19. Now in this case, what you should have found was 3 times 4.5 is 13.5, and this is greater than the clear layer height of 8.5 metres, so you've got to use a coefficient of 0.21. If it had been greater, if the clear layer height had been greater than this, you'd have used the lower value of 0.19, but in this case, you should have used 0.21. Now you're putting your known variables into the formula. You should have got a mass flow rate of smoke of 93.7 kilograms a second. That's how much smoke this fire is going to develop. So we've got to know how much smoke. Now we need to know how hot it's going to be. Let's move on to step 4 using this formula to work out the temperature of the smoke using theta equals QP divided by MC, where theta is your temperature rise, your QP is your convective heat output in kilowatts, M was your mass flow rate of smoke, and your C is your specific heat capacity of air. If you'd have put them in, you should have got a theta value of 86 degrees Kelvin. That's what you should have got. That's the temperature increase, but you need to know now the absolute average temperature of the smoke layer using this formula here. TL equals TO plus theta, where your TL is your absolute average temperature of your smoke, TO is your temperature of ambient air, and your theta is your temperature, is your actual temperature increase. Put them in, you'd have got a TL of 374 degrees Kelvin. So we know how much smoke we've got and we know how hot it is. Now we need to know how we're going to start to extract this smoke. Now before determining this, we have to consider stratification, and this is covered in step 5, the stratification check. Now in this building, due to having such a low clear layer height, we've got 8.5 metres, stratification is not going to occur at that level. You're looking at 8 stories high, you've got to look at quite high figures for stratification. So in this case, you can actually ignore step 5, you don't have to carry it out. You can move straight on to step 6, which is determining the ventilation requirements. Now you could use either natural ventilation or mechanical ventilation. Now in this case, mechanical ventilation has been decided on. So now we need to determine how many reservoirs we need. So we've got mechanical ventilation. How many reservoirs do we need? Well, the largest size of reservoir in a mechanical system is 2,600 square metres. However, this can be increased to 3,000 for property protection only. So you can increase it if it's only for property protection. This is to do with your travel distances. Now the size of the building is 200 times 90, which is 18,000 square metres. Now if you divide this by the maximum size here, which is 3,000, gives us 18,000 divided by 3,000, gives us 6 reservoirs. So you need a minimum of 6 reservoirs. However, you've got another rule to satisfy. Don't forget the 60 metre rule. You can't have any dimension longer than 60 metres. Based on the parameters, as you can see here, we need at least 8 here. Yeah, you might need 6 to meet the requirement, but based on these parameters here, you can't have one more than 60 metres long. So in this case, we're actually going to have to increase it. We need 8 reservoirs. That's what you should have worked out, 8 reservoirs. Now next, because we're looking at mechanical ventilation, you don't have to determine the aerodynamic free area of vents in the area. You have to work out the volumetric flow rate in each reservoir, and this is based on your design fire size. To determine the volumetric flow rate, you use this formula here. V equals M divided by rho times TL divided by TO, where your V is your volumetric flow rate in metres cubed a second, your M is your mass flow rate of smoke in kilograms a second, your rho naught is density, TL is your absolute average temperature of the smoke, and TO is ambient air temperature. If you'd have put those in, you'd have got a volumetric flow rate from each reservoir of 101.4 cubic metres a second. That's what you need out of each reservoir, the volumetric flow rate of any fans. So in each reservoir, we need to extract at least 101.4 metres cubed a second. Next one you've got to look at is step 7. We need to work out how many fans we need. Now, we know that the proposed fans have a capacity of 10 metres cubed a second. We know the volumetric flow rate is 101.43 cubic metres a second. So if you divide it out, you need 10.14 or 11 fans. You're going to need at least 11 fans in each reservoir to satisfy that volumetric flow rate. However, because this is a storage facility, it is usual to discount a fan. Because you're storing things right near the fans, you could assume that the flames might actually take out a fan where the fire is. So you've actually got to have one more. You've got to assume one's taken out. So in your calculations, you've got to assume there's at least one extra. So you've got to have at least 12 fans in this situation. So we are going to need 12 fans with an output of 10 metres cubed a second as we worked it out. Now that covers step 7. Now we're going to move on to step 8, which is a stagnation check. Now remember, with mechanical ventilation, there is no requirement for stagnation, so you can go straight on to step 9. It only applies to natural ventilation, so you can go straight on to step 9, which is the plug hole in check, which applies to both natural and mechanical ventilation, the plug hole in check. Now don't forget, there's 2 models to determine if plug holing will occur, and this will depend on where the venter is located. Now the model to use when the ventilator is more than 2 metres from the edge is as follows. This is the formula here. Now if you put all your known variables in, you should have got an MCRIT of 35.52 kilograms a second. That is the maximum smoke that can leave each fan without plug holing occur. 35.52 kilograms a second. So if more than 35.52 kilograms a second leaves each fan, it is likely to plug hole. We now need to determine how much smoke is likely to leave each fan. We know that each fan is rated at 10 metres cubed a second. We now need to know, if you convert this to a mass flow rate, what's going to be leaving. And this is the formula to apply. Now that's each fan. If you'd have put that in, you should have got a critical rate of 9.24 kilograms a second. So each fan is likely to be extracting 9.24 kilograms a second. We worked out the critical exhaust rate for each fan was 35.52 kilograms a second. So in this case, plug holing is unlikely to occur. It's not going to occur. That covers that step. Let's move on to step 10 now, which is working out your air inlet velocity check. The final check that has to be done is to ensure that the replacement air coming in through the exit doors is not so high as to impede escape from the building. Now this is a warehouse, so on the assumption that only staff resort to the building, the maximum velocity that is allowable for the incoming replacement air is 7 metres a second. Now we do not have a figure for the area of the inlet vents that will provide replacement air, so we're going to calculate the minimum required area. Now if all the fans are working, in other words, none's been lost due to the fire, due to its proximity, and you've got to assume this, there's 12 fans extracting 10 metres cubed a second. And this gives us a total extraction rate of 120 metres cubed a second. Now if you put those in this formula here, the AI must be greater than or equal to this formula here to work out the velocity. You should have got an AI greater than 28.57 square metres. This tells you that you need at least 28.57 square metres of inlet air to replace the air that's been extracted. So you've got to provide that and make sure it's below the smoke layer. So there's got to be at least that area to get those people out of there. The final step, move on to step 11, which is the post-design considerations. In this case, you've got to consider weather conditions. Again, tall buildings may have an impact on it. And there's no smoke curtains in this particular case. If not, you've got to be careful they don't deflect. In other words, carry out your post-design considerations, testing, maintenance, etc. That completes this exercise.